Hello everyone, and welcome right back. Let's dive straight in, shall we? Welcome to the 20th explainer in our ongoing research methodology series, titled Types of Hypothesis. Today, we are focusing on a topic that is honestly the absolute beating heart of scientific inquiry. If you're doing any kind of research, and I mean whether that's for a university dissertation, a corporate market analysis, or an independent scientific study, you really need to think of a hypothesis as your trusty compass. Seriously, imagine wandering aimlessly through this dense, pitch-black forest of data. You're totally unsure of which way leads to your actual destination. Well, a hypothesis is that essential tool that keeps you on track. It points you directly toward what you actually need to find. Without it, you're just kind of collecting information at random, hoping something, anything makes sense eventually. But with it, you have a clear, highly focused path forward that guides literally every single decision you make.
Okay, let's get into our taxonomy of inquiry for today. To make sense of what can feel like an overwhelming list of terms, we are going to organize these into logical families. We'll start with the foundation, then look at hypotheses by complexity, by direction, by statistical testing, and by research method, before finally wrapping up with choosing the right one.
All right, part one, the foundation. What exactly is a hypothesis? Before we can categorize them, we have to be crystal clear on our starting point. Its primary job is to take a broad, messy, real-world problem, the kind of incredibly complex issues we see in everyday life, like trying to improve a country's education system or understanding global health trends, and convert it into a highly specific, testable statement. Note that word, testable. According to renowned researchers Kurlinger and Lee, this isn't just a random guess you make over a cup of coffee. No way. It is a carefully formulated proposition. It has to be based on existing theory, previous research, or solid logical reasoning. This tentative statement becomes your compass. It directly guides your data collection, dictates your choice of research methods, and ultimately sets the entire stage for your final analysis.
I absolutely love this academic anchor from Good and Hat. They define a hypothesis as a proposition that can be tested to determine its validity. This highlights a truly vital distinction for us. Untestable opinions absolutely cannot function as scientific hypotheses. Let me give you an example. If you say, education is valuable, well, that's a wonderful thought, but it is a general opinion. It is way too vague to measure because, let's face it, valuable means very different things to different people. But if you take that exact same sentiment and instead say, students who attend school regularly score higher in examinations than students with poor attendance, boom, now you have something empirical. You can actually measure attendance by counting the days present. You can measure scores by looking at the grades. You can look at the hard evidence to see if your statement holds true. That is the magic of a good hypothesis.
Let's move to our second family and see how this builds when we start looking at how many variables we are juggling. Section 2, by complexity.
The distinction here is beautifully straightforward. A simple hypothesis predicts a relationship between just two variables, one independent variable, which is the cause, and one dependent variable, which is the effect. For example, regular exercise reduces stress. It's direct, it's super easy to isolate, and it is highly focused. But, on the other hand, a complex hypothesis predicts a relationship among more than two variables. Because let's be real, human behavior and the natural world are rarely simple, right? In the social sciences particularly, we are constantly using complex hypotheses. For instance, predicting that parental education, family income, and school environment all independently influence a student's academic achievement. A student's life isn't just about one single thing. Here, we're juggling multiple variables simultaneously to capture a much more realistic, layered picture of the world.
Transitioning now to our third family, we look at hypotheses grouped by direction. Let's see how specific our predictions can be.
A directional hypothesis doesn't just say two things are related, it confidently predicts exactly how they are related. It tells you if something will go up or go down, score higher or score lower. For example, predicting that increased screen time is associated with lower sleep quality. See what we did there? We are clearly pointing to a negative outcome. We are taking a firm stance. Now, a non-directional hypothesis simply states that a connection exists, but it purposely leaves the exact outcome open. For example, saying there is a relationship between study time and academic achievement. Does more study time make achievement better or somehow worse? We know they are deeply connected, but the exact direction is left as a mystery to be solved. We acknowledge the link without making any assumptions about the final result.
So, why choose one over the other? Well, this brings us to a really important guideline from Creswell and Creswell.
You shouldn't just guess a direction for the fun of it, or just because you have a personal hunch. You should only use a directional hypothesis when previous research or a solid theory gives you a highly justified reason to predict that specific result. If previous findings in academic journals are just a mixed bag, or maybe you're doing brand new exploratory research in a completely unstudied field, it is much safer, and honestly vastly more scientifically accurate, to use a non-directional hypothesis. Doing this prevents you from accidentally biasing your own research from day one.
Now, what's really interesting about this next grouping is how it forms the actual basis for mathematical evaluation in quantitative research. Section 4, by statistical testing. In statistics, you always have this fascinating pair dance between two hypotheses. The null hypothesis, which is symbolized as H0, assumes that any difference you see in your data is just due to random chance. It basically states that absolutely nothing special is going on and there is zero significant effect. The alternative hypothesis, symbolized as H1 or HA, is its logical opposite. It boldly states that a significant relationship or effect actually does exist in the real world. Now here is the twist that kind of confuses a lot of beginners. Researchers actually design their statistical tests to evaluate the null hypothesis. We essentially put the nothing is happening theory on trial to see if our evidence is strong enough to reject it. We do this because in science, it's often much easier to disprove that nothing is happening than it is to conclusively prove every single aspect of your proposed theory. If we can confidently reject the null, only then can we support our alternative hypothesis.
And this brilliantly illustrates an absolutely crucial point from the statistician Andy Field. If your test results come back and you fail to reject the null hypothesis, it does not magically prove that absolutely zero relationship exists in the universe. It simply means your specific study didn't find enough evidence to prove it this time around. Think of it like looking for your misplaced keys in a dark room using a very weak flashlight. Just because you didn't find them doesn't mean they aren't somewhere in the room. Maybe your sample size was too small, or your measurement tool was a bit weak. It's a vital distinction that reminds us that science is an ongoing process, and frankly, it keeps researchers very humble.
Moving right along, let's introduce our fifth family, categorizing hypotheses by how they fit perfectly into specific real-world research designs.
Let's walk through these. First, we have the associative hypothesis. This predicts variables are connected, which is perfect for correlational research. But guys, remember the golden rule here: correlation does not equal causation. Just because ice cream sales and shark attacks both go up in the summer doesn't mean eating ice cream causes shark attacks. They just happen to move together. Next is the causal hypothesis. This goes a massive step further. It predicts one variable actively influences another, which is the strict domain of experimental research using highly controlled environments and control groups. Then we have the descriptive hypothesis, which predicts the frequency of a phenomenon, like estimating the average stress levels of local public school teachers. This is absolutely perfect for broad surveys and needs assessments. Finally, the working hypothesis. Think of this one as your rough draft. It's a provisional guide for the early stages of exploratory research that just helps organize your thoughts before you have all the hard facts in front of you.
It's also vital to see how hypotheses differ between entire research paradigms. Quantitative research relies heavily on rigid, formal hypotheses created strictly before data collection begins, mostly because they're required for those mathematical statistical tests we just talked about. Qualitative research, however, usually begins with broad research questions. According to Creswell and Poth, in qualitative studies, hypotheses are often emergent and inductive. This means they're highly flexible. They evolve and naturally emerge during the actual data analysis process as the researcher slowly uncovers hidden patterns. It's very much like a detective carefully putting together clues as the investigation naturally unfolds.
Section 6. Choosing the right hypothesis. So the crucial point here is how you take all this incredible information and practically apply it to your own work.
Think of these criteria as your personal, handy mental checklist for your next project. Ask yourself, are you testing a direct relationship between just two things? Keep it clean, use a simple hypothesis. Are you dealing with multiple messy, overlapping factors in human behavior? You're going to need a complex hypothesis. Does existing literature give you a clear, undeniable theory on what will happen? Go ahead and use a directional hypothesis. Are the outcomes completely uncertain or highly debated in the scientific community? Play it safe, use a non-directional hypothesis. And if you are running statistical tests through any kind of software program, you absolutely must frame your predictions as null and alternative hypotheses. Remember, a well-formulated hypothesis is the very backbone of your entire study. A poorly formulated one, it just creates cascading confusion from start to finish, muddying your data and totally ruining your analysis.
So, what does all this mean for you? I want to leave you with a provocative question.
What hypotheses will you use for your next research project? Take a moment today to really think about the core problem you want to solve and start drafting that tentative, testable statement. If this explainer helped clear up the confusion around hypotheses, please take a second to like this explainer, drop a comment below with your thoughts, your project ideas, or any questions you might have. Share this with your fellow researchers to help them out, and be absolutely sure to subscribe to the channel so we can keep this methodology journey going together. Thank you so much for learning with me today, and I will see you in the next explainer.